So my talk is about reasoning about types in code, and the first thing I'd like to say is that I'd like to make it much more precise than what usually people say. You probably have all heard that programmers reason about code or something like that, but this is very imprecise. Everybody reasons about everything at all times. You need to be much more precise, especially as functional programming has a very specific kinds of reasoning that are not available for other paradigms of programming. So even people who write deployment Perl scripts, they have to reason about those Perl scripts, and they have to be logical and precise about those scripts, but this is not functional programming. So I would like to be quite precise about what exactly we need to know as functional programmers, and what kinds of reasoning and tools for reasoning we need to use. And the examples of reasoning about types, for instance, designing a data type for a specific application. And sometimes you can simplify a type by reasoning about it. You can say that this data type is equivalent to a simpler one, and it represents the same information, but it's simpler to use. And this simplifying transformation is exact. There's no opinions about it, it's mathematics. And so you can reason mathematically about equivalence of types. Another thing you do in functional programming is you use different type constructions, what I call type constructions, for example. You take two types, you make a pair of them, or you take an either of them, or you have a function from one type to another. Functional programming has 6 fundamental type constructions, such as these 3 that I just said, and these are what I mean by type constructions. So you need to learn how you can use them to make different types for different applications. All right. Reasoning about code is another thing that we do. So one example would be that you have a certain data type which has the properties of a monad, but you want to verify that. Or you have some other type class and you want to derive the implementation that satisfies the laws. So this derivation again is mathematical. It's quite precise. It's like a proof. Another example is that you're simplifying a function. You have a function, and another one is equivalent to it, gives the same results, and is simpler. So you can derive that. Learning how to reason about this requires a very limited amount of mathematical knowledge. It is mostly at the level of polynomial algebra, arithmetic, and very, very little abstract algebra. It is really not graduate level math at all that you need. You need more or less undergraduate level introductory math to learn how to do it. Now, I felt that there isn't a very good source of information about how to learn these things. So people are writing tutorials online, explaining to each other what a free monad is and so on, because there isn't a book that explains it. And you read this and you're not satisfied, so you write your own tutorial, which other people are not satisfied with, so they write their own tutorials. Now, writing a free monad tutorial is just as popular as writing other tutorials like this. So I'm writing a book, which is not ready. It's about half of what it will be right now. I just printed the draft. This book will explain in my own very detailed and boring way, but it will explain. So not like this. Okay. So this is not an explanation. This is a joke. Just so that you know, explanation is different from this. Explanation means you will actually understand after you read the explanation, right? So it's not like, oh yeah, this guy is so clever, I have no idea what he said. But no, actually what I want is to explain with examples and details and exercises which are doable, and not like, oh, derive something I'm too lazy to derive as an exercise. No, that kind of thing is not an exercise. I want to do actual exercises that are doable to show what techniques we have for reasoning about types in code. How to do symbolic calculation with code, so you can derive the laws or you can verify the laws in basically pen and paper way. It's not some kind of framework or formal method. It's just pen and paper, like school algebra. And I give always real-life motivations for these techniques. So why you want to write this code comes from real life. So these laws, they don't fall from the sky, and they don't fall from nowhere. They come from actual programming tasks. You want to do an aggregation on something, whatever, filtering. What are the laws of filtering? I'd like to know. Did I implement my filtering correctly for a new data type? I'd like to know. To know that, I need reasoning. So that's what this book will teach. Now, this book will be free in the sense of the Free Software Foundation. The entire source code is free and under an open source license. So which means you can print it yourself, you can make changes to it, you can reformat it, whatever. It's a free license. So I will give some examples of these reasoning tasks very quickly with no derivation right here, just for you to understand what kind of things you can do once you learn these techniques. So first example is, can you implement these functions f and g that I have written? So you're given a value of type function from R to either ZA, and you want to compute either of Z function R to A. Now this looks very abstract, but often you have the either type that models errors, and you have a function that returns a value which could be an error, and so on. So can you kind of expand the error handling like this, so that the function that gives you an error becomes an errorful computation with a function inside, or not? Or can you do the other way around? So imagine you're making a library, or you're writing your application, you're trying to transform these types like that. So it turns out that F cannot be implemented. G can be, so here's a code for G, but F cannot be implemented. And the thing is that it's not just because I'm not clever that I don't know how to implement F. It cannot be written, so this code does not exist. There's some reason why you cannot do this. It's a mathematical reason, which is not obvious, and as an engineer, you should be able to recognize that. You don't necessarily have to prove from first principles, but you have to recognize this. So you have to know that these things exist, and you have to stay away from them, obviously. Maybe you don't want to spend a week trying to implement this function whose code does not exist. Another example that my colleagues often ask me about, you try to combine computations that return a future and computations that return an error. So how do you combine them? You write a for yield block, but a for yield block must have a fixed type constructor on the right-hand side of the arrows. So you cannot combine like this, but you want to, because some of these computations return a future and others don't. They return an error maybe. And so how do you combine them? Now, one way of combining them would be to have a different data type that wraps an either and the future at the same time, such as either of Z and future A, or maybe future of either ZA. So which one of them is right? Well, I want to wrap this in a case class maybe and implement a flat map for it, then I can have a for yield with that case class. But which one is right? Now here's, again, as an engineer, you need to recognize that, first of all, there is a choice here, which is unambiguous. Either of z future a is wrong, because it will not implement flat map correctly. Again, why? It's a long story, but this is a derivation that you can do, and as an engineer, you need to know that you've done it at some point in your studies. You don't want to derive this every time from scratch, obviously, but you have to recognize. So, for those who know, this is a monad transformer, but you need to remember at least that this thing exists, that one of them is wrong, and you shouldn't try to use it. If you try to use it, you will have very strange bugs in your program. Another question. Here's my data type, option of a triple of AAA. Can I implement a flat map for it? I can implement a map, but I want to use that in a for yield block, so I need a flat map. Can I implement flat map? And the answer is no. I can actually implement a function with the right type signature of flat map, but it won't satisfy the laws of the monad, and nobody knows why. Nobody knows why. You know?
No, not a clue.
Okay. You tell me if you know. Because nobody knows why. You can prove that this is so, but nobody can explain what's wrong with this type. Why is it not behaving like a monad? What's wrong? Option of A is a monad. We know that. So what's wrong with this? Nobody knows that. But you need to understand that such things exist, stay away from them, or not stay away from them, but just don't think you can make a monad out of this, because you can't. Another example, I want to have a future. Now, we know a future can be chained as a monad, but I want to have a twist on it. Now, each of these future computations could fail, and I want, because of the business logic of my application, I want to be able to clean up the failures. So what does it mean to clean up? It means each operation comes with a cleanup code, and when the chain of futures has a failure at some point, I want to execute all the cleanups in the opposite order, in the reverse order, automatically. I don't want to write special code for each time. I want to have automatic cleanups. How do I do that? So one way of doing this is to have a type future of pair of A and a unit-to-unit function. The unit-to-unit function represents a cleanup, and then I write flat map like this, which appends the cleanups, and I recognize that the cleanups form a monoid, so I can append them. I have one unit-to-unit, another unit-to-unit, I can append them, and this cleanup will be executed automatically in the order I want. I don't have to worry about it. And so I implement this flat map that appends the cleanups and executes the cleanup when there's a failure. And this type will guarantee that whatever chain of features I make with this flat map, with this flat map, of course, not with the standard one, all the cleanups will be automatically run in the opposite order. Another example is a free monad. Now, I will go through this example in much more detail later. It's a different definition of free monad that people have made, and the question is, what's the difference? And the final example is how to define a free monad which is generated by a pointed functor, which is a functor that already has the pure method. So the monad needs a pure and a flat map, and the pure is already there. So can you somehow use that in the free monad? Can that free monad be simpler or faster or something? So these kind of questions are the questions that require reasoning about types and code. In order to make this reasoning practical, I developed a notation, which I will summarize in the next two tables very quickly. So this table is a type notation. So instead of writing Scala syntax for types, I write these kind of, what you see in the right column of the table, some kind of mathematical looking formulas where types, the type parameters are just letters, the tuples are products, the ethers and case classes are sums, so I call them disjunctive types because they model disjunction of different possibilities. So they're written as sums, the function type is written as an arrow, the unit type or any kind of named case object or something like this is just a 1, and so on. So for example, this type constructor option of a triple is written as 1 plus a times a times a. And I have type parameters that are written as superscripts. Oops, this is not great. Okay. Here are examples of reasoning tasks that are done with this notation. And you see, this type equivalence is just like arithmetic. So you very easily get used to this. And instead of writing either of pair of either and so on, it's just very long. You write formulas like this. And then you use arithmetic intuition, at least for sums and products. For functions, you need to develop a different kind of intuition because functions they're not arithmetic operations, and they have special rules. Arithmetically, they are more like power, exponentiation, but it's inconvenient to use exponentiation when you compute. It's very inconvenient. It's much more convenient to use the arrows. So I have a lot of examples of how to reason about this, but basically these are type equivalences written in this way. And to reason about code, I have a notation for code, which is like this. So I have, again, I have some symbols that I use. For example, instead of saying left and right in either, I do a plus 0. So either is A plus B. If you have a left of A, it means you don't have a B. So I put a 0 instead of that. Now, I don't know if this is the best notation ever, but I've done a lot of computation, a lot of derivations, trying to change this notation whenever necessary to make my life easier. So I think it's pretty good, but certainly there are other opinions. I have another notation for type of values. So for example, here is a function f, which has the type a to b to a. I write this type as a superscript with a colon. So that's kind of reminds me of Scala's colon, but it's in the superscript. So the result is that it's much more visible. F is visually much clearer. A superscript you can kind of ignore much more easily if you need to. A very important part of my notation is that instead of saying dot map, I write a superscript with an arrow. Oops, I can't find my mouse right here. Oh no. Computer. Behave. Okay, so the up arrow, it means the lifting of a function into a type constructor, and I write the name of this type constructor next to the arrow to remind myself which type constructor it is. Otherwise, it's kind of very confusing. You're lifting all over the place. What is the type constructor? If you just have one, it's okay. Usually you don't have just one. So, as a result, I can reason about equational laws, about equations, much more easily. I have much less to write, and it's much more visually clear what things can be combined. So, for example, I use the triangle, which is in some programming languages, you actually have this triangle, which substitutes argument on the left into the function on the right, which seems kind of strange. But in Scala, you have this all the time. You have x.filter x.map, x.this, x.that. You substitute x into a function which is on the right all the time. And actually, it's very good to have notation for this, and it's very good to have a short notation for this when you're reasoning about code. Okay, so now I will spend the next 15 minutes going through some advanced examples. So feel free to, relax and check your email. Okay, so the first example. At some point, I was quite confused by the free monad. By the way, just to give you a context, in 2015, free monad was quite widely accepted by the Scala community. But this was not the case in 2013. So somewhere between 2013 and 2015, somebody made it so. I don't know who that was. There were certain people giving talks about the free monad, but this time, I think maybe it was Runar who did it in 2014. Just what I'm saying. So, Gabriel Gonzalez is a Haskell guy who had a blog post about the free monad in 2012, and if you translate his stuff into Scala, it will look like that. Runar gave a talk in 2014 in Scala, and he defined the free monad like this. And Kelly Robinson gave a talk in 2016, and she defined the free monad like that. Okay, so I was quite confused when I first looked at this. So what is the free monad? Which one of them? Are they the same? Or maybe some of them are actually not right. How do I even know what that is? What do these things do? So in order to reason about them, my first step would be to rewrite them in the type notation so that all these names go away, all the syntax goes away. So here's what I find if I rewrite this in the type notation. The first definition looks like this. Free of ft, free one of ft, is t plus f of free one of ft. So when, instead of two case classes, I have just a plus, and the first one is just t. So I strip away all the names, this pure, flattened t, f, all this is gone. I just see the types, because the names are convenient for a programmer, very convenient, but completely unhelpful when you reason about the properties of types. These names have nothing to do with the properties of types. You don't want to write them, especially when you do calculations. The fewer symbols you have to write, the better. So the first, therefore, is t plus f of free one of ft. Oh yeah, and the superscript is the type parameter. So it's f of free one of ft. And the type parameter is a superscript. The second definition looks like that. T plus an existential qualifier on A. Now, why is that? Why did I not use any existential qualifiers for the first one? Well, the reason is, if you look at this definition of bind, the type parameter A does not occur in the type parameters in the class we're extending. So we're adding one more type parameter in the case class, but this type parameter is invisible outside. So when we create a value of this case class bind, we have to choose this A. But once we have done it, nobody will know what we have chosen. So and in the type notation, it means this type is hidden. It exists inside this value somehow, but we don't see it. And in the type notation, this is expressed by writing this existential qualifier. There exists an A, a type A, so that we have a value of type f of A product with A to 3 of ft. So that is how you denote this kind of thing. And the type notation shows you very clearly that the role of the type parameter A is different, quite different from the role of other type parameters. And this is not obvious when you look at the code. Look at the code, there are all these things, you don't see that A actually has a completely different role. And there's a huge difference when you have this A. And the third definition is the longest one. It has 3 case classes, so I have a disjunction of 3 possibilities, and therefore I have something plus something plus something, and so on. So now I can reason about this. The first definition actually assumes that the type constructor f is a functor, and the second definition does not assume that. In order to see that otherwise they would be equivalent, we need to use something called the Unida identity. And the Unida identity is a type equivalence, which I have written here, which is that if you have an existential type and an expression of this form, that is equivalent to this. Okay, so this is a very non-trivial identity, which you have to derive, have to understand what it means, how to use it, and it's far from trivial. So it's not kind of something I can just explain in 5 minutes. But you learn it, and once you learn it, you just say, oh, I have exactly this structure on the right-hand side here. And so I can just put instead of B, this. And then I can simplify one type into another, and then I have exactly equivalence between these two things. And this is only true when f is a functor. So I can find by this reasoning, which is purely mathematical, there are no tests I have to run, it's just completely mathematical, and it's not very complicated. I'm writing a bunch of gibberish, but it's not so complicated once you learn what these things do. So I have found that the first 2 definitions are actually equivalent given that f is a functor. So that gives me very good information as a programmer. So if I have a functor, I'll use the first definition, but if I don't, I'll use the second one. Otherwise, I'll have the same thing. So they're equally good, but I just can use one or the other. And the definitions 2 and 3 are also equivalent, but in a different way. The definition 2 and 3 both require that f should be a functor. But actually, the definition 3 it has 3 case classes, and the definition 2 has only 2 case classes. So they have different memory requirements, different performance characteristics. And actually, Kelly Robinson's talk explained that. So she was talking about the performance of this free monad and so on. But other than that, are they equivalent? So this is a computation that I could explain in about 5 minutes. I don't know if you want to listen to this, but I would just say how this is done. So I'm writing a formula for this type. And this type is recursive, so free 3 is defined in terms of free 3. It's a recursive formula. And because of this, I can use induction, and I can substitute free 3, which is this, into this. And so this gives me a way to transform the formula. Then I have a product of a sum, so I can expand the brackets, just like in arithmetic. And then I do things like that. And I see Unida in here, by the way. And so I just keep doing this kind of thing, and I reason about it, and I use the monad's law. So if I use monad's law to transform, let's say, flat map of flat map into composition of 2 flat maps, then I can see that basically some parts of this can be replaced, and then I get from definition 3 into definition 2. So, long story short, the computation, it is not so easy, but it doesn't take you a week. And once you have done this, you understand definition 3 is actually equivalent to definition 2. The free monad will be eventually evaluated to some specific non-free monad for which the laws hold. And so assuming the laws is okay. You can always assume that they hold. You'll never see any violation of the laws once you have interpreted the monad. And so at this point, they're the same. So they might not be the same in terms of performance. The code is quite different. So then you should say, okay, good. So I can use each one of them according to performance characteristics. So then I go back into Kelly Robinson's talk to understand that. So that's the kind of reasoning that you do in this case. So let me finish with another example, which is more complicated. I like complicated things. I don't know about you. So this example is a reasoning about the so-called selection monad. I'm not sure anyone has ever heard of that. And I haven't, until I stumbled upon this interesting type, which is monad in A. Not trivial and not clear what you use it for. There is a paper about search monad, which has a different type, which is like this, and it kind of shows you a search. So this is a predicate. You want to find the values A that satisfy this predicate, and you might have found them or not. So this is a result of the search. Okay, well, it doesn't really convince me so much. Maybe it's useful. But interestingly, there's not much about this monad in the literature. In Haskell, there's something completely different called the search monad. I don't know. It's not clear to me that a lot of people are using this. So, the point of this example is that reasoning about this monad is hard. Okay? Here's a paper, which I'm linking in here. And this paper talks about the transformer of this monad, selection monad transformer. So how do you find a transformer? So they say, well, this is a transformer. But it's not enough to say, you have to prove. And they can't prove. So here's the quotation from the paper. The proof that the selection monad satisfies the law was found using a computer program. The author verified that the transformer preserves the unit laws. Well, those are the easy ones. Yeah? But the proof of the associativity law appears to be unmanageable. The author is currently working on a formally verified proof that this law is satisfied. All right, well, good luck. Because if you don't know how to prove it by hand, I don't think a computer will help you. Very often you can't just guess how to prove it using a formal tool like a computer proof assistant or something like that. So why was the proof too hard? So my guess is that they were trying to do it in the programming language syntax, like Haskell syntax. Writing it out is incredibly tedious, and you get stuff that you can't read, and you don't know what to do with it. So the law is this must be equal to this. Okay? What do you do with this stuff to transform one into the other? You don't see anything about it. You know, it's all a bunch of brackets and arrows, and you have no idea what to do. So, and by the way, the author doesn't know how to prove it for the selection monad either. They use the computer program. So if you use the notation that I developed, you can prove this in 5 lines of calculation. So let me show you the 5 lines. Okay, these are the 5 lines. Starting here, well, this is a definition of something, and these are the 5 lines. I'm not joking. I'm not. This is, like I said, this is a joke. This is not. Okay? So what do you do? Well, it's a selection monad transformer. First you write down its type. So in my notation it is like this. Now, if you want to define, first of all, you want to define what is the monad function for it, or flat map or something like that. Well, it's hard to define. You look at it, you don't know how to define. So intuition you can get if you look at the Kleisli functions. So the Kleisli functions are functions with the type signature a to mb, or in this case it will be a to tb. So a to tb is like this. Now if you look at this a to b to mr to mb, it's kind of awkward, but there's a trick. You can flip the first two arguments. So this is a curried function, it has two arguments. You can flip their order. If you flip their order, and you have a function like this, b to mr to a to mb. Now this function looks like from one Kleisli to another. And that's the key. Because now you can use the Kleisli composition in the M monad with these things. So let's denote by the diamond. So diamond M is the Kleisli composition in the M monad, and diamond T in the T monad. So how do you define the diamond T? You define it using diamond M twice. Why? Well, you can reason about it by saying, well, first I need to get F, which is this, from B to MR, A to MB, into C to MR, B to MC. So now how do I combine these things so that I get what I want? I need C to MR to A to MC. So then you combine like this. So you begin with a function k, which is C to MR. You apply G to it, you get B to MC. Now, B to MC and C to MR can be combined using the Kleisli. You get B to MR. B to MR is this. Now, this is going to be an argument of F. You get A to MB, and you already had B to MC, so you're done. So this is the result. And then we assume that the M is already lawful, so its associativity law is satisfied. And now we just need to compute associativity law for T. We write it out. This is just, we prepare this to be used for later, and then we just put it all in. Associativity law on the left-hand side, and the right-hand side. And you just need to substitute and write out. So you have a very long expression, and another very long expression, but it's exactly the same one. Now, that's how the proof goes. You have to, of course, you have to do it, but this is not so bad. You know, it's just, you put it in, and it's all working out. Okay. So
if the Kleisli composition is associated with the underlying transformation.
So I have proved, assuming that this holds for diamond M, I prove that it holds for diamond T. So I prove that this is equal to this. This is the associativity for diamond T.
Okay, but if diamond T is associated with T associated?
So T is the monad I'm trying to construct. And so I need to define the diamond T, and I need to show that it's associative. Once I've done this, I have proved that T is a lawful monad. So this complicated type I have proved for any monad M to be a lawful monad. So this is a monad transformer of the selector monad. And by the way, the selector monad has another transformer, which looks like this. And you again can derive this and prove this very quickly. So this is an interesting example of a monad that has two different monad transformers, not equivalent, with different properties. Nobody knows what to do with this. I'm not claiming I know what to do with this, but if you have a complicated type like this, and you're able to just do it, you completely lose fear. I have another t-shirt, don't fear the monad. This is the way to lose fear, but this is a hard way to lose fear. So, let me conclude. In my view, you would need about 6 months to lose fear. They're a hard way, but it's permanent. You will never get afraid again. You just.
How many hours a day?
I don't know. You have to work on your fear. So the book I'm writing is going to be very, very difficult. So it's full of explanations, calculations, examples, exercises. I don't know. Certainly harder than any book I've read. Yeah, but it explains. You see, the other books, why are they hard? Because they don't explain. They don't say. They tell you something as if it's easy, and you look at it for a week because it's not easy. They don't explain. Why don't they explain? I don't know. Maybe they don't know how to explain. But the fact is, that's why it's hard. Now, if you have a lot of explanation, it takes a long time to go through it. I don't know what's better. But you have a choice. And it's free. I mean, you can download for free. You can print yourself. This is not expensive, but it costs money to print. So why print if you can just download it? Don't buy it. Read it, but don't buy it. Come on. It's 21st century. You're not supposed to put books on paper anymore, right? It's all directly downloaded into your brain. So 6 months of downloading into your brain, you'll be able to use functional programming much more effectively than before. You know, a colleague comes to me and says, how do I stop? I know. I know. This is a monad transformer, don't worry, I know what it is. No, seriously, that's what it is. Functional programming is an engineering discipline. It requires study. Unlike Perl scripts, they don't require study. You just look at Perl scripts, you write another Perl script. Functional programming requires study. You have to think, look at things like math, whatever. In the book, I have all this. Right now, first 7 chapters already. And if you have any questions about like what that is, that won't be in the book. You know, this kind of thing, it's just a joke. It's useless. What you need is to have actual experience working with monads. I mean, all these, remember this example? The type that, oops. What is this? What's going on? All right, somebody had imperative code on there. Yeah, this example. No, I'm serious, nobody knows why this is so. You can't have a monad for this. But you will be able to prove it. You'll be able to have some kind of intuition. I have very little intuition for this, but I have some. Yes. I would say, oh yeah, this is not a monad. It's all going to be explained in the book. Well, thank you very much for your attention, and I hope you have enjoyed what I was presenting.
Thank you, Sergey. Questions?
Do you use these techniques, these reasoning techniques, in the code that you write at work?
The question is, do I use these techniques? Do I use these reasoning techniques in the code that I write at work? Very, very infrequently. So first of all, these techniques are reasoning before you write the code. So if somebody comes to you and says, we won't need to write this code, then you would go take pen and paper, write something and reason a little bit, maybe 5 minutes, and the rest of the month you're writing code. So that's how it is. I mean, you don't often need to do this. But the example with futures and cleanups, this is a real example. This is not the code where exactly what we used, but we had to implement this, and I had to look at some reasoning before suggesting solutions to my colleagues. So yes, occasionally, but certainly it's far from something to do every day. But similarly, an engineer doesn't spend the entire time in computing mathematical equations. An engineer spends a little time doing it, and the rest of the time is doing engineering. But so one of my main points here is that functional programming is actually like engineering. It's actually similar to engineering. Unlike writing Perl scripts, which is not similar to engineering, this is similar to engineering. You do some kind of calculation, and then you write code. I hope I answered your question.
I noticed you have a lot of tutorial videos on your YouTube. If I do have 6 months, which one should I start with your videos or the book?
So the question is, if you have 6 months to study this, should you study the videos or should you study the book? You should study both, and also 3 other books.
Any 3 books? Any 3 other books?
I don't have, no, not by me.
And the 3 other books?
Sorry.
Sorry, you said study the videos, your book, and 3 other books.
Correct.
Any 3 other books, or do you have 3 in mind?
Well, so there are a few books that I have in mind. So one of them is the red book, Scala, Functional Programming in Scala. It is really very similar in spirit to what I'm trying to write, but my writing is much more boring. So I would even say, yeah, start with that if you haven't read it. Read the book. Videos are much slower. They have a lot of code. Videos have an advantage. They have more code than this book. You can already read this. These first 7 chapters are in good shape, quite readable. You can start with that. Let's see if that takes you 6 months. Hopefully not. And by that time, more chapters will be available.
The other 2 books?
So, I think one is called Functional Programming for Mortals. And it's yellow. Sorry, it's green. So this is a red book, green book, so this is going to be yellow. Okay? Certainly easier than, well, anyway, it's really going to be good. There's one more book, which is called something like Calculating Programs, or Programming by Calculation, or something like this. It's Haskell based, but it's also in the same kind of vein, but it has much less code. So, I mean, that's about all I know. So all these books are books about functional programming as engineering. First you learn, I mean, imagine an electrical engineer who wants to build an antenna. Electrical engineer first makes a calculation, some kind of Fourier analysis, some kind of whatever. I'm not idea what they do, but they have some calculations, and then they do the antenna design. They don't start the antenna and write tests for it, right? No, before you do that, you do a calculation. What calculations do we do as software engineers? These ones. That's my main point. There are actual calculations, small ones, not used every day, but actual calculations you can do that help you write code. That's what my book is about. So the books I'm talking about are kind of trying to do the same. There are lots of books about functional programming that don't do this. So that's what I mean.
Also, if you find Sergey on LinkedIn, he's written a fantastic article comparing engineers with artisans. And that resonates with what you're saying right now a lot. And I've shared it multiple times on Twitter and LinkedIn because it resonates with me a lot. Highly recommend that.
Can you go back to the previous example of like you can't do a flat map on a triple? And you already said no one knows why, but can you give a little more explanation? It seems like you should be able to do this.
Yeah, so the question is, can I explain why we can't define flat map on a triple? It's an optional triple, and we can define a flat map, just won't satisfy the laws. Just return none. You can define the function that returns none at all times, right? It will satisfy the type signature, but not the laws.
Right.
So I have only one piece of intuition about this. Are you familiar with monad transformers? Do you know the reader monad? Yeah. Do you know what the monad transformer is for the reader monad? Okay, it's too bad. Unfortunately, this will be in my chapter 9, and I'm not ready to start writing it yet. Yes, so the point is, the triple AAA is very similar to a function from a type with 3 values into A. Now that is very similar to a reader monad, where we read from a type with 3 values and return A. Now, if you wanted to combine option with that, you would have to put option inside and the reader outside. That is how the monad transformers work. And that's for a reason, because if you put them the other way, the laws don't work. Now, if you try to write down option of Z to A, where Z is some type, you will not be able to define either for that also. You will not be able to define flat map that satisfies the laws. So this is just kind of an intuition that reader has to work in this way. Option has to work in this way. You try to do it in the other way, you fail. For reader, you can prove that it works. For option, you can prove that it works. It's very hard to prove that something doesn't work. Because for this thing, there are dozens of implementations that you can write down, and they all don't work. So how do you prove that nothing works? You go through all of them. Okay, and then I have option over quadruple, and so on. It's a huge amount of work. I don't know how to explain why it will never work, but it will never work. So the intuition that you get is that you look at the triple, you recognize that this is like a reader monad, and the reader works in a specific way, has to work in that way. So then you're done. So then you say, okay, well, yeah, I talked to a professor from Great Britain, and I asked him, and he has no clue. So I said, do you know that this is not a monad? What? Oh, why? Trying to find a reason for that is satisfying. He did not find one. It's hard. I'm not sure anyone knows this today. But the point is, engineers have a lot of stuff that nobody knows how it works, but they know it works, and so that's how we engineers must continue. So there's some intuition, and there's some mathematics, and there's a lot of experience, and that's how engineers work. So see, this is an example that is puzzling. There's a Stack Overflow discussion about option of a pair, which is also doesn't work. It's similar, it just still doesn't work, and people are discussing and they say, but why? But why? Here, well, yeah. I mean, I'm very confident that it is correct because several people checked it. And it's a mathematical computation. So in principle, you could formalize it in a proof assistant and have assurance, mathematical assurance in the system.
I'm wondering, is there any kind of connection you see between this approach that you have and like propositions as types and intuitionistic type theory, a la those kind of work that mathematicians have done from that side?
So the question is there a connection between this reasoning and propositions as types and the intuitionistic type theory? So very little of what mathematicians have done needs to be learned in order to be able to do these things. So one kind of reasoning that you can do is, for example, my example one, for this one. Y, so functions f and g, if you translate them into intuitionistic logic, you get formulas of logic that are not valid, not theorems. And we can prove that using tools of logic. And so the types as propositions means that this type cannot be implemented. So these tools of logic are hard though, they're not easy for programmers to use. And I would not use them because it's too hard. Too much work, so you need kind of tooling. Also, this problem is not often seen, and it's very easy to develop intuition that just tells you, oh, don't go there, don't try to do this. Here's an intuition here, for instance. You want to take a function from R to either, so it can return left or right for different R's, and you don't know which. But you have to return an either, which will be for all R's. You can't do that.
Yeah. This one's intuitive.
Right. So this kind of intuition is clear. And then you say, oh, but maybe I'm not clever. Maybe there's some trick. These functional programmers, they always come with tricks, you know. Maybe I'm not clever enough. Maybe I need to read 5 more tutorials and something. So you need to know that this is actually possible to do this. And this intuition is actually correct. So you need to develop your intuition. So that is an example where you would use intuitionistic logic if you wanted to be rigorous and mathematical and have a proof that this is impossible.
Well, this is really amazing. So is it possible for one day someone create a static code analysis to us just by looking at our method signature and just saying that, no, this code is wrong, although it's functional. But if there's a bug in some edge cases, you never touch.
So the question is, can we have tooling to examine type signatures and do some kind of reasoning and discover bugs or edge cases that the code does not touch? This kind of thing would be very, very difficult. So right now, what you can do is you can have a tool that tells you that F cannot be implemented, and a tool that tells you that G can be implemented and generates code for G automatically. You can do that. But it's very difficult to write a type signature that expresses edge cases or some kind of value dependent propositions. And this would be necessary to use dependent types if you wanted to do that. Now that is much harder. So writing a program that expresses as a type some kind of property and then checks that property automatically, not by tests, but symbolically, that's a very hard thing. So I would say that there are very limited uses of this in simpler cases where you can do dependent types. It's very hard to do that in general. So for actual work, you say, okay, well, here I have reasoning, but in more complicated cases, I would write tests. I would do reasoning, but I would also write tests. The CATS library comes with tests for laws, for example. So you can run those tests on your data structure. Imagine you have some business logic dictated by your project manager, and you want to implement a monad on it, right? You cannot change this business logic. So how do you check that your monad is right? Maybe it's not right, then you can't, then you know what to do. It's very hard to write a tool that would do this automatically. And remember that example I gave at the very end? There was a paper where they used a computer program to prove something about one monad, but they could not prove a more complicated thing. And I don't blame them. I mean, it's exceedingly hard to do that, to have a tool that will prove things for you. So there are certainly applications of this. But finding bugs, actual difficult to find bugs, and edge cases just from the type signature, that's hard.
Great, we only have 5 more